Okay, now we're going to introduce some of the other variables that we use to calculate Q, or heat flow. And the first variable we're going to talk about is specific heat. And there are several ways to abbreviate this. Whoops, didn't mean to do that yet. You might see just S, SP, H, SH. I tend to use SPH. And basically the specific heat is unique to a substance, and it's the amount of heat required to raise the temperature of 1 gram of that substance by 1 degree Celsius. And these have all been experimentally determined, and you can look them up in a table. But we can also calculate them from experimental data, which is how we made the table to begin with. I do want to add something here, though, a reminder that this is at constant pressure. And specific heat has units of joules per gram degree Celsius, so 3 different units. This is also what we call an intensive property. What does that mean? Intensive properties are independent of the size of the sample. Okay, so it doesn't matter how much you have, you'll get the same result. Heat capacity, on the other hand, represented by a capital C, of a substance is the amount of heat, or Q, required to raise the temperature of a given quantity. So this can vary, or the mass can vary, of the substance by 1 degree Celsius. This is an extensive property. So the size of the sample matters. Okay. So we have a table here, some specific heats of some common substances, and you'll see joules, grams per grams degrees Celsius. And you see, notice most of these are under 1. Some are greater than 1, but they tend to be smaller values. And we can calculate, we'll calculate heat capacity, excuse me, by multiplying mass times specific heat. Okay, that's one way to get heat capacity. And that means that, I want to make sure I don't write over something that I'm going to pull up later. Mass, and I'm just using the units here, times specific heat. Grams would cancel, so your heat capacity will be in joules per degrees Celsius. Now the equation for calculating heat flow, or Q, is Q equals mass times specific heat times delta T. That mass is in grams because now if you look at these units, mass is in grams, this is degrees Celsius, grams and degrees Celsius will cancel, so our Q will always be in joules. Sorry, I'll erase that. So it's Q can also be calculated by multiplying heat capacity by delta T. And delta T, of course, is calculated by subtracting T initial from T final. So another term we need to introduce is a variable that describes heat flow that occurs at constant pressure, which is what we are working at here on Earth. Consistent gravity. So we have a constant relatively constant. So it doesn't fluctuate so much that it affects chemical reactions. And that is called enthalpy. And it is designated by the capital letter H. We can also, this is a state function, delta H equals the enthalpy of products minus the enthalpy of the reactants. So if we have the enthalpy for our reactants and products from a table, which we can look up, they've been experimentally determined, we can calculate the change in that heat flow into or out of the system as it occurs under constant pressure. So again, delta H is the heat given off or absorbed during a reaction at constant pressure. We're given two enthalpy diagrams here from bottom to top. We've got an increase in enthalpy. And on the left-hand side, we're looking at the process of solid water being converted to the liquid water. And in order for that to happen, the solid water has to absorb heat. So this would be an exothermic reaction. I'm sorry, endothermic. I'm not paying attention. So the system is the ice. It's absorbing heat from the surroundings, so it's endothermic. And if you recall, Q for an endothermic reaction is positive. So delta H will also be positive. And we see that delta H given right here. And notice that these, and when you look them up in the table, are given in kilojoules per mole. On the right-hand panel, we have condensation reaction, or phase change from gaseous methane to, oh, actually, this is a reaction, never mind, not a phase change, but it's a chemical reaction. And you'll notice the delta H here is negative. This is combustion. What is one of the products of a combustion reaction other than CO2 and water? Heat. So heat is given off. So heat is released to the surroundings, which again is exothermic. So Q is negative and delta H is negative. So this is an example of what a coffee cup calorimeter looks like. And again, we call this constant pressure calorimetry because the pressure is constant. We have discussed delta H and delta Q with respect to phase changes and chemical reactions, but not how we determine the values. And we do that using coffee cup calorimetry. And that's the experimental approach for measuring heat flow associated with these processes. And the device, of course, is called the calorimeter. So this is an insulated system. We have two styrofoam coffee cups. One of them contains water. There's a thermometer, there's a stir in here, and the reaction occurs in here. So because of this cap or top, no mass leaves the system, and because of the insulation of the sides, we do not transfer heat. So there's no heat transfer because it's insulated. No heat transferred. from the cup, that is. The heat is transferred within the solution in here, not to the surroundings out here. And of course the cap, there's no mass transferred or vapor. Okay. So, starting with first law of thermodynamics, Q of this system is going to equal Q of the water plus Q of the calorimeter plus Q of the reaction. And Q of the system, equals 0. So remember, this and this can be rearranged and to denote the heat transfer within that system. So we can also say then that if Q of the system equals 0, Q of the reaction equals negative Q of the water plus Q of the calorimeter. But the Q of this calorimeter is negligible, so it's not considered. So what this boils down to is, I'm going to write it over here, Q of the reaction equals negative Q of the water. And Q of the water equals the mass of the water times the specific heat of the water times delta T of the water. We could also calculate Q of the calorimeter, but since this is an insulated system and it falls out of our equation, we don't need to consider that. It is such a small number. So for reactions at constant pressure, then delta E will equal Q of the reaction. Okay? So, enthalpy of solution, or delta H of a solution, is the heat generated or absorbed when a certain amount of solute dissolves in a certain amount of solvent. So this is a solution. And delta H of the solution equals H of the solution minus H of the components. And this is basically the same as Q of the reaction because it's at constant pressure. So we could also say that delta H of the solution is equal to Q of the reaction. And over here we have a table of heats of solution for some ionic compounds. And again, they're given in kilojoules per mole. You can look these up in a table. They've been experimentally determined. And this question asks which substance or substances could be used for melting ice. So if we want to melt ice, we want something that's going to give off heat, right? What do we use on our roads in the wintertime? Some kind of salt. So these compounds with negative delta H's would be useful for melting ice. Obviously, calcium chloride is going to be better at it. It's got a higher delta H than the lithium chloride. How about substances that could be used for a cold pack? So here we want a substance that's going to absorb thermal energy, cooling, and that would be ammonium nitrate. It's got the most positive delta H here of solution. So there are also practical applications when we're looking for substances to perform different things for us, like melting ice or putting a cold pack on a sprained ankle, things like that, or a bruise, a black eye, whatever. So let's talk a little bit more about dissolving substances. So if upon dissolving, two things could happen. The solution becomes cooler, solution becomes hotter. So if the solution becomes cooler, which means the temperature goes down, the reaction is endothermic. So delta H of that solution is positive. If that solution warms up, or the solution becomes warmer, which is detected by an increase in temperature, the reaction is exothermic. And delta H will be negative. And so for solids and gases dissolved in water, the volume of the solution equals the volume of the water, but the mass of the solution does not equal the mass of the water. And that's because the specific heat of water is much, much greater than the specific heats of solids and gases. And the mass of the water is much, much greater than the masses of solids and gases. So once again, we can say that, Q of the reaction equals negative Q of the water. So we base that Q of the reaction on Q of the water. So Q of the reaction then is going to equal negative the mass of the water times the specific heat of the water times the delta T of the water. Okay? And this is applicable for solids and gases dissolving in water. Okay, we're going to do an example problem here. I'll read the problem. In a coffee cup calorimeter, 3.00 grams of potassium nitrate is dissolved in 50 grams of water. The temperature of the solution changes from 27.6 degrees to 25.1 degrees Celsius. We're asked to calculate the heat energy for the process and the heat of solution for 1 mole of potassium nitrate dissolving in water, and then classify the reaction as either exothermic or endothermic, and that is going to be determined by the sign of Q and delta H. So Q of the reaction equals negative Q of the water, which equals negative the mass of the water times the specific heat of water times the delta T of water. We need to calculate delta T, and delta T equals T final minus T initial. So delta T equals T final is 25.1. T initial is 27.6. So our delta T is a negative 2.5 degrees Celsius. We were subtracting here. We need one decimal place in our final answer. You need to know the specific heat of water. Memorize that. Specific heat of water is 4.184 joule per gram degree Celsius. And we're given the mass of the water in the actual problem. So Q of our reaction equals negative mass of the water, which is 50.00 grams, times the specific heat of water, times the delta T. Don't forget your negatives and positives here. Makes a big difference. Celsius, degrees Celsius cancel, joules cancel. Excuse me. So Q of our reaction will be in units of joules, but we have a negative in front of this equation, and we have a negative in the equation. So we are going to have a positive Q of the reaction, and that is 523 joules. So that's the amount of heat that was absorbed from the water in order for that potassium nitrate to dissolve. Okay. Technically, we can only have 2 sig figs in this answer, but we're not done with our problem yet, so I'm not going to round that yet. I'm just going to mark it. If this were all we were asked to calculate, then I would write this in scientific notation. 5.2 times 10 to the second joules. But we're not done, because we're also asked to calculate the heat energy for the process and the heat energy or heat of solution for 1 mole of potassium nitrate. So now we have to calculate Q of the reaction for 1 mole of KNO3. And we just calculated the joules that were absorbed when we dissolved 3 grams of KNO3 in 50 grams of water. So here we're just using dimensional analysis. I'm going to convert the 3 grams to moles, so I need the molar mass. Ooh, and this gives me 17,608 joules per mole. Mark that there. So I still need 2 sig figs in my final answer. So I could treat this one of 2 ways. I could write this in scientific notation, in which case it would be 1.8 times 10 to the 4th joules per mole. Or I could convert this to kilojoules, and I would do that by converting those joules to kilojoules, and there are 1,000 joules in 1 kilojoule, which would give me 18 kilojoules, and that would be per mole of KNO3. Okay? All right, now we're going to look at the process for determining the specific heat of aluminum using coffee cup calorimetry. And as I said before, all of these tables have been built experimentally. I mean, the delta H's, the Q's, or the specific heats have all been determined experimentally. So how do we determine the specific heat of a metal? We're using aluminum in this example. So the mass of aluminum beads that we're going to be using is given 23.50 grams. Then we bring a beaker of water to boil. Boiling point of water is 100 degrees Celsius. And add the aluminum beads and boil for 10 minutes. During that 10 minutes, we are assuming that the aluminum or the metal beads absorb heat from that hot water and come up to the same temperature. So we are assuming that T initial for our metal equals 100 degrees Celsius when we start our experiment, or at the end of the 10 minutes of boiling. While that's working, we're going to place a measured amount of water in a coffee cup calorimeter. And the volume that we put in this calorimeter had a mass of 130.0 grams. And we take the temperature of that water. So this is T initial of the water, and that was 23.0 grams, or degrees Celsius, sorry. So after we have heated those beads for 10 minutes and assume that the temperature of the beads is 100 degrees Celsius, we add those metal beads to the water in the calorimeter and close the lid. And then we start monitoring the temperature. So the water temperature is going to rise as the heat transfers from the metal to the water until thermal equilibrium is reached and this temperature stops rising. And that will be T final. And that was recorded as 26.0 degrees Celsius. So again, we're going to use the first law of thermodynamics, and we can say that Q of the metal plus Q of the water equals 0, which means we can also write this as Q of the metal equals negative Q of the water. That's easy, right? So Q of the metal equals negative mass of the water times specific heat of the water times delta T of the water. We have to calculate delta T, which again is T final minus T initial. So our delta T equals T final for the metal is 26. I'm sorry, for the water. Oh, I'm going the other way. T final for the water is 26. Yeah, I was right. I was confused in my head. T final minus T initial of the water, which was 23 degrees Celsius. So our delta T for the water is 3.0 degrees Celsius. We've memorized specific heat of water. And the more you practice these types of problems, the more the easier that memorization gets. So now we can calculate Q of the metal, negative mass of our water is 130 grams times 4.184 joules per gram degrees Celsius times our delta T of 3.0 degrees Celsius. So, we've got to answer the question in the last problem, and we were supposed to indicate, or at least I think we did, whether that was exothermic or endothermic. And I was reminded because I was just thinking about delta T here. So if delta T of the water is negative, that means it's an endothermic reaction because we end up with a positive Q of the reaction. If delta T of the water is positive, then we have an exothermic process. And we'll have a negative delta T. Not delta T, Q of the reaction. Geez. All right, let me move on here. Okay, so doing that math, let's see. This is 1,632 joules. Grams canceled, degrees Celsius canceled. We are limited to sig figs by our temperature, which has only one decimal place. And this is negative. Sorry, didn't put the negative sign there. So Q of the metal is negative 1,632 joules. So this is the heat that was gained by the water or the surroundings that the system gave off, okay? The metal gave off heat to the water, so it's a negative Q of the reaction or Q of the process. So we know what Q of the metal is. Now we can calculate or determine specific heat of the metal. Q of the metal equals, metal equals mass of the metal, specific heat of the metal, times delta T of the metal. And we know what Q of the metal is. We just calculated it. So negative 1632 joules. I don't think I allowed another slide for this. I'm going to try to cram it in here. The mass of our metal is 23.50 grams. The specific heat is what we're trying to find. It's unknown. And now we have to calculate delta T of the metal. Delta T of the metal is going to be negative. So T final for the metal is 26 degrees, and T initial for that metal is 100 degrees. So our delta T for the metal is a negative 74.0 degrees Celsius. Okay, now we're just going to rearrange this and solve for specific heat. So specific heat equals negative 1632 joules divided by the mass times the delta T. So in our final answer, we end up with units per gram degrees Celsius, and we've got a negative in the numerator and the denominator, so specific heat will be positive, and specific heat is always positive. If you get a negative, you have a sign problem somewhere. And this math works out to be 0.938. We're restricted to 2 sig figs, so this rounds to 0.94 joules per gram degrees Celsius. Yeah, I'm glad I stayed on that and finished it up. So here's another practice problem. We have a metal sample weighing 33.4 grams at a temperature of 95.8 degrees Celsius. It is placed in 169 grams of water in a coffee calorimeter, and the water in the initial temperature of that water is 24 degrees Celsius. At thermal equilibrium, the temperature of the water and the metal is 27 degrees Celsius. Determine the specific heat. So once again, the heat lost by the metal is going to equal the heat absorbed by the water. So Q of that metal equals negative Q of the water. And that's the first step in determining the specific heat of the metal. So Q of our metal, negative the mass of the water, 169.0 grams, specific heat of water, joules per gram degrees Celsius, 4.184, delta T of water. So T final of the water is 27 degrees minus T initial of 24. So our delta T is 3.0 degrees Celsius. And Q of the metal equals negative 212, whoa, what's going on there? 2121 joules. It's restricted to two significant figures, which again I'm going to mark. We'll not round till the end after we've determined the specific heat of the metal. So again, Q of that metal now equals the mass of the metal times the specific heat of that metal times the delta T of the metal. We know the mass of the metal. We just determined the Q of the metal in the prior calculation. Our mass of metal is 33.4 grams. We're looking for specific heat, and we need to calculate delta T of the metal. T final of that metal was 27 degrees. T initial was 95.8, and these are degrees Celsius. So T of the metal is a negative 68.8 degrees Celsius. Rearranging to solve for specific heat, we have negative 2121 joules divided by 33.4 grams times negative 68.8 degrees Celsius. Again, negative divided by negative gives us a positive specific heat. We get 0.923 joules per gram degrees Celsius, but we're limited to 2 sig figs, so we have to round that to 0.92 joules per gram degrees Celsius. So practice these. I think they're fun. I hope you have fun learning them, how to work them. So one more discussion about calorimetry that I do not test on, but I want you to be do know something about, or at least I don't test on using calculations. I might ask questions about how this differs from coffee calorimetry, which is, again, calorimetry that's at constant pressure. So if you think about it, for those combustible materials, we couldn't do that type of calorimetry in a styrofoam cup because they explode. They're explosive. They're explosive reactions. They change the pressure. So this is called constant volume calorimetry or bomb calorimetry, and it is used to determine heats of combustion. And this is something you should remember. And I'm going to basically just walk through the components here in the setup. If you look at the calorimeter itself, or the apparatus, I should say, because this is where the reaction occurs, and this is the actual bomb. So this is where the reaction takes place. And outside that bomb, and it's not insulated, but it's constant volume. So this can burn and exert a pressure against the walls of that bomb. And it can transfer heat to the water in the calorimeter bucket. So this is the calorimeter bucket in which there's water that heat can be transferred to. That's where the thermometer is located. There's an insulating jacket around this as well. And anything else I'm missing? No, I don't think so. Okay, so the sample is placed in that sealed bomb, and which is capable of withstanding high pressures that are a result of those combustion reactions. And surrounding that bomb, well, the surroundings are the bomb, the water, and the vessel in which they are contained in the calorimeter. And that's what I meant when I said this is not isolating. Heat can be transferred from the reaction to the bomb to the water. And so this is calculated a little differently. Each calorimeter, or the bomb, has its own heat capacity that's unique to that particular bomb calorimeter, and it has to be determined experimentally. But when you calculate Q, whoops, that's not what I meant to do. Calculate this. I'll give you a shorter version of this in a minute. But Q of the system equals Q of the water, Q of the bomb, Q of the reaction. Okay? No heat enters or leaves outside this insulated jacket. So Q of the system equals 0, and Q of the reaction equals negative Q of the water plus Q of the bomb. Okay? So, and of course, Q of the water is calculated as we always calculate. And Q of the bomb is that heat capacity of the bomb times delta T. So that's where we get this value. This reaction occurs, again, at constant volume, but not constant pressure. So remember, delta H equals Q of the reaction at constant pressure, but pressure is not constant in bomb calorimetry, so delta H does not equal Q of the reaction. It may approximate it, but it does not equal it. So that's all you need to know about bomb calorimetry or constant volume calorimetry. It's used for heats of combustion. Pressure is not constant, but volume is. And we're going to move on to thermochemical equations.